MS Ramaya University of Applied Sciences.
Hi students, let us discuss viscometers. Aim of the experiment is to determine the viscosity of a given oil at different temperatures using Seybold and Redwood viscometers. The term viscosity describes a material's property in terms of a fluid's thickness. It is a measure of a fluid's internal flow resistance or the resistance to being deformed. A fluid's viscosity is determined by viscometry. All materials range on an imaginary scale from solid to liquid. Solid materials are specified as elastic, while liquids are viscous. Most materials are not purely elastic, nor entirely viscous, but viscoelastic. Depending on their properties, substances can be classified as viscoelastic solids like gels or viscoelastic liquids like hair shampoo. Viscometry deals with ideally viscous fluids and with certain limitations also with viscoelastic liquids, that is viscous substances with an elastic portion. If a fluid flows easily, its resistance to deformation is low. It is a low viscosity fluid. Fluids with greater resistance to deformation do not flow easily. They are highly viscous. A low viscosity fluid fills more volume than a high viscosity fluid for a given time and given temperature. According to Newton's law of viscosity, the shear stress, tau, on a fluid element layer is directly proportional to the rate of shear strain. The constant of proportionality is called as the coefficient of viscosity mu. The relationship is given as tau is equal to mu into du by dy, where tau is the shear stress in Pascal, mu is the absolute viscosity of the fluid in Pascal second, and du by dy is a velocity gradient in a direction perpendicular to the flow direction having the units of second inverse. Kinematic viscosity is another term in defining the viscosity of the fluid and is defined as the ratio of the dynamic viscosity to the density of the fluid. It is denoted by nu, and the equation is given as nu is equal to mu by rho, where nu is the kinematic viscosity of the fluid in meter square per second and rho is the density of the fluid in kg per meter cube. A viscometer is a device used to measure viscosity of a liquid. The different available viscometers are rotating cylinder viscometer, falling spear viscometer, efflux viscometer, and capillary tube viscometer. In efflux viscometers, the viscosity is determined by noting the time of efflux under specific conditions for a fixed volume of fluid through a specific capillary or aperture. The different available viscometers based on this principle are Seybold, Redwood, and Engler viscometers. For calculation purpose of kinematic viscosity, the simplified expression is obtained as nu equal to A into T minus B by T into 10 to the power minus 6, where nu is the kinematic viscosity,
meter square per second.
T is the time in seconds, and A, B are experimentally determined constants which are different for different efflux viscometers. A Seybold viscometer is an efflux type viscometer in which viscosity is determined as a function of time. It consists of an orifice and a capillary having 1.76 mm diameter and length of 10 mm through which the oil is allowed to pass. Time in Seybold seconds is defined for collection of 60 ml of liquid to flow out of orifice. A rubber cork is provided to stop the flow of liquid. To calculate the viscosity using the expression of efflux viscometers, the constants A and B are specified as 0.226 and 195 respectively if the time is less than 100 seconds. If time is more than 100 seconds, A is taken as 0.22 and B as 135. A redwood viscometer is another efflux type viscometer that works on the same principle as that of Sebald viscometer. It consists of an orifice and a capillary having a diameter of 1.62 mm and a length of 12.25 mm through which the oil is allowed to pass. Time in redwood seconds is defined for collection of 50 ml of liquid to flow out of orifice. A needle ball valve is provided to stop the flow of liquid. To calculate the viscosity using the expression of efflux viscometers, the constants A and B are specified as 0.247 and 190 respectively, if the time is less than 90 seconds. If time is more than 90 seconds, A is taken as 0.264 and B as 50. In this image, we can see the difference between Sebald and redwood viscometers. A stopper is used in Sebald viscometer and a needle valve with a ball point is used in case of redwood viscometers. Typical values of dynamic viscosities of some commonly used fluids are shown in the table. It can be observed that the dynamic viscosity of water is 1 pascal second, whose comparison can be made for lower and higher viscosity fluids like petrol and oil respectively. At Ramaiah University of Applied Sciences Laboratory, the density of the fluid at the given temperature is calculated by measuring the empty weight of collecting flask and the weight of the flask with oil. Dynamic viscosity can be further calculated by using the kinematic viscosity obtained from efflux viscometer as the product of kinematic viscosity and density of the fluid at that temperature, which is given as nu is equal to nu into rho.
Hello everyone. Today we shall calculate the viscosity of oils using redwood and Sebald viscometers. This is the setup to calculate the viscosity using redwood viscometer, and this is the Sebald viscometer. For the redwood viscometer, we use a collecting flask, which is also called as a Kohlrausch flask, which is having a volume of 50 ml, and for the Sebald viscometer we use a collecting flask of 60 ml volume. This is the setup of redwood viscometer. At the center of the viscometer we have an oil cup, inside which we shall collect the oil whose viscosity has to be measured. On the outside of the oil cup, it should be stored with water. Now the water has already been filled on the outside of the oil cup. It has to be filled up to the brim. We can also observe a coil which is used to heat the water. We shall take the 20W40 SAE oil, which is used for 4-stroke engine lubrication. Let us calculate the viscosity of this oil. First, we need to pour the oil into the oil cup. The oil has to be filled up to the marking given in the oil cup. Next, we need to measure the weight of the empty 50 ml flask used for the redwood viscometer. it is showing a value of close to 34 grams. After the oil is filled up to the mark in the oil cup, we shall close the oil cup with the lid provided. Next, we need to place thermometers, one thermometer to measure the temperature of the water and another thermometer to measure the temperature of the oil. This is a needle valve's handle. Now, if we pull the needle valve up, the orifice at the bottom of the viscometer opens up and all the oil starts to flow down. This shall be opened once the temperature of the oil has reached a desired value. Now we shall heat up the oil by heating the water first using the coil inside the water jacket. The coil will be switched on by the heater. We shall switch on the mains of the heater and start by giving some voltage regulation. Now, as the water is being heated up in the redwood viscometer, we shall repeat the same procedure for the Seybold viscometer. Just as in the case of redwood viscometer, even in the Seybold viscometer, we have an oil cup inside which we shall collect the oil whose viscosity has to be measured. On the outside of the oil cup, we have provision to store water, and inside the water there is a heating coil which is used to heat the water, which in turn heats the oil. The water has to be filled up to the brim. Unlike the redwood viscometer, which had a needle valve, the Seybold viscometer have a cork at the bottom of the viscometer. So once the cork is opened, the orifice will allow the oil to flow down. Now let us fill the oil cup of the Seybold viscometer with the SAE 20W40 oil. Just as in the redwood viscometer, we shall measure the weight of the empty flask for the Seybold viscometer. It is showing a value of close to 32 grams. Once the oil is filled in the oil cup, we shall close the oil cup with the lid, and then we need to place thermometers to measure the oil temperature and also to measure the water temperature. This temperature gauge will give the temperature of the water, while this temperature gauge will give the temperature of the oil. Now we shall start the experiment by switching on the electrical supply for the coil. And let us switch on the voltage regulation and keep it close to 60 or 70. On the redwood viscometer, the temperature of the oil has reached 40 degrees Celsius. Now at this temperature, let us calculate the viscosity of the oil. In order to do that, first we need to lift the ball valve. Now as we open the needle valve, the oil starts to flow from the orifice and gets collected in the coal roche flask. Once the needle valve is opened, simultaneously the stopwatch has to be started. Now the oil is being filled up in the collecting flask. As the oil approaches the 50 ml mark on the collecting flask, we need to stop the needle valve and also stop the time on the stopwatch. Now this is the oil collected in the collecting flask of exactly 50 ml volume. The weight of this oil along with the collecting flask shall be measured. We can see a weight of close to 72 grams of oil and the collecting flask. By taking the difference of this weight with the weight of the empty flask, we can get the weight of the oil collected in the flask. In the Seybold viscometer, we have kept the oil for heating. Now the temperature of the oil is approaching 55 degrees Celsius. At this temperature, let us calculate the viscosity of the oil. In order to do that, we need to first open the cork at the bottom of the viscometer, which will allow the oil to flow through the orifice into the collecting flask. Simultaneously, the stopwatch has to be started. Now, as the oil is being collected in the flask, it is approaching the 60 ml mark. As it reaches the marking, we need to stop the oil flow by closing the rubber cork and simultaneously stopping the stopwatch. Now the oil has been collected in the collecting flask, which measures exactly 60 ml. Let us go ahead and measure the weight of the oil. The value of the oil along with the flask is showing close to 86 grams. By taking the difference of this value with the previous value of the empty 60 ml flask, we shall get the value of the weight of the oil collected from the Seybold viscometer. We know that as the oil or any fluid becomes more and more viscous, it becomes very difficult for the fluid to flow. Hence, for a particular volume of the fluid to flow, it shall take more time if the oil is viscous. Whereas if the oil is having lower viscosity, it shall take lesser time to actually flow the same volume of the fluid. And we also know that at higher temperatures, the viscosity starts reducing. So by this experiment, we can repeat for different temperatures on both the viscometers. Now once the time and the weight are noted down, we can calculate the kinematic and the dynamic viscosity of the oils at the respective temperatures. And that shall conclude the experiment.
At MSR UAS, we spark your imagination unlike any other.